The continuous time analog audio signal XT recorded from the degraded telephone channel is converted into a discrete signal XN via uniform periodic sampling. The processing parameters are established at a standard communication sampling rate of S equals 8,000 Hz, corresponding to a uniform sampling interval of Ts equals 125 microseconds. This relationship is governed by the fundamental mathematical formula xn equals xt, where t equals nts. This discretion process populates our digital database array in MATLAB, translating the analog acoustics into accessible numerical values. The resulting discrete time waveform plot reveals structured speech enveloped clustered within distinct sampling rates. However, a continuous wideband baseline fluctuation persists across the entire sampling duration, indicating heavy deterministic noise corruption. Looking at raw time samples alone cannot isolate the specific noise frequencies, dictating a transformation into the frequency domain for spherical diagnosis.
Hassam from Home Group 1. Today I'll present DTFT, the spectral diagnostic. To identify the distinct frequency components of the background noise, the discrete sequence undergoes a fast Fourier transformation to compute its magnitude spectrum. This process represents a finite computation of the discrete time Fourier transformation, DTFT, defined by this mathematical formula. Our frequency domain plot reveals a dominant sharp interference spike located precisely at 100 Hz with a magnitude approaching 300, identifying it as a low frequency electrical line hum. A crucial speech fundamental component is simultaneously observed near 250 Hz because this 250 Hz peak represents vital vocal frequencies. A broad high pass filter would muffle the output noise. This dictates the design of a highly selective digital notch filter centered strictly at 100 Hz to isolate the noise from the voice. Thank you.
Filter coefficient synthesis requires evaluating the trade-offs between week 13 windowing method and week 14 bilinear transformation. Although the bilinear transformation yields a highly compact infinite impulse response filter, its recursive nature introduces nonlinear phase responses that cause phase mirroring and echoes in audio signal. To preserve speech intangibility, the windowing method is selected to design a finite impulse response notch filter. An ideal non-causal band-stop impulse response (SGN) is multiplied by a symmetric 151-point Hamming window (WN), producing a deterministic linear phase impulse response vector B that prevents phase distortion. The relationship is mathematically represented by Hn equals Hdn times Wn. By writing the exact windowing equation directly into our custom scripts, we bypass internal toolbox dependencies, ensuring our code generates perfectly stable, reproducible coefficients.
Okay, so to verify the structure integrity and safety, we actually use the impulse response and change it into transfer function. So how we do it? Do it using the Z transform. Okay, so from Z transform, once we change it, the equation that we got, we can have it as a visual representation in Z domain. Okay, which is what you're looking at right now. So because it's an FIR feed forward operation, is the denominator polynomial is structurally A equal to 1. So all 150 systems is actually all 150 systems poles is at the absolute origin. So it's at Z equal to 0. So since the system is causal, so the ROC is extending outward from the Z equal to 0 from the origin. So it encompasses the entire circle boundary, yeah, means under than Z over 1. And then all poles, it resides strictly inside the unit circle as well. So it's all under 1 as well. So the filter can be verified as unconditionally stable, which means it guarantees that it will never produce recursive mathematical overflow or any acoustic clipping.
So now with the time domain convolution and performance verification. So the final real-time noise attenuation is executed in the time domain via discrete linear convolution. And the corrupted input array is convolved sample by sample with the finite filter impulse response through a causal difference equation. So our post-filtering verification plot demonstrates the absolute success of the DSP pipeline, and the destructive line hum spike is entirely flattened down to baseline level. Meanwhile, the vocal fundamental peak and its corresponding speech harmonics are perfectly preserved, yielding a clean, high fidelity and intelligible audio output. All access has have been formatted precisely in physical units to fulfill the mapping criteria, and uh, it has completed a rigorous end-to-end digital signal processing solution. So that's all for me. Thank you so much.